Thin lens and magnification equations. Thin lens equation is used to calculate the location of the image, whereas the magnification equation tells us about the image characteristics. There's a sign convention that we have to go through. From the lens maker equation, we now know that the focal length that's positive is a converging lens. If it's negative, it's a diverging. Sign convention for objects are, if I get a positive object, that means that's a real object and it's on the left side of the lens. However, there is such a thing called a virtual object, and that object is on the right side of the lens. However, this virtual object only occurs for a two-lens system. We'll talk about this when we deal with two-lens systems. For the image, if it's positive, it's a real image formed on the right side of the lens, where if it's negative, it's virtual, and it's formed on the left side of the lens. The last thing we got to talk about now is the magnification. A lot of information packed in the lateral magnification. What we do know here is that if I have a real image, they're always inverted. If I have a virtual image, they're always erect. And that becomes important in trying to understand that when you look at the sign of the magnification. Sign of the magnification implies the following thing. If m is positive, the only way m could be positive here is if the image distance here is negative. So if the image distance is negative, then that means it's on the left side, so it's virtual and I have an erect image. On the other hand, if the magnification is negative, then that means that the only way that could be true here is if the image distance is positive, but if it's positive, it's on the right side of the lens, so therefore it must be real and it's an inverted image. Let's go to the magnitude now. Magnitude of the magnification implies the following thing, that if this value is less than 1, I have a smaller size image. If this value is equal to 1, I have a same size image. And if this value is greater than 1, I have a larger image. But there's more to it if we start to look at the ray diagrams with this equation. The key point to understand is one compares the distance of S prime to S to understand why an object size is the size that it is. Ray diagrams. Let's focus on a converging lens. What you see here is that the object is really far away from the lens compared to the image distance. The fact that S prime is smaller than S implies then that the magnification is then going to be less than 1. Once again, since S prime is less than S, then that implies here that the magnitude of the magnification is less than 1 and I get a smaller image, just as the ray diagram shows. Now if I come over here to the lens where the object is at 2f, we see that the image is also at 2f. Because they're the same distance, that means that the magnification will be 1 and I have a same size object here. The last two lenses we could see here is that when the object is in between 2f and f, this distance here is shorter than the S prime distance. So therefore, because S prime is bigger than S, we then have a larger magnification. Now, if the object is inside the focal point, I compare the distance S to S prime again, you could see that S prime is farther away from the lens. So therefore, I should have a larger image. We go on to the next example. Example 34.2. An object stands on the central axis of a thin symmetric lens. For each situation, determine the missing pieces and draw a ray diagram. So looking over here at the table, lens right here tells me that I have to determine what type of lens is it. Is it converging or diverging? The focal lengths, the object locations, the image location, the magnification, and then identify whether the image is real or virtual and whether it's erect or inverted. So let's start with lens number 1. The magnification is greater than 1. The only way you can have a magnification greater than 1 is if the lens is converging. So focal length 1 is equal to plus 20 centimeters. Now, to determine the image location, I use the thin lens equation. Solving for S prime is going to equal to SF divided by the quantity S minus F. Substituting in the numerical values, I get an image location of minus 13 centimeters. Now I'm going to use the magnification equation to get all the image characteristics. Magnification is equal to minus S prime over S. Its sign and its magnitude will tell me about the image. Putting in the values, I get a magnification of plus 1.7. Now let's interpret that. Plus sign indicates that the image is erect and virtual. The magnitude, being 1.7, implies that the image is larger. In other words, the image height is equal to 1.7 times the height of the object. Now, drawing in the ray diagram shows that with the focal length of 20 centimeters, the object at 8 centimeters, then that image is going to be inside the focal point at 13 centimeters. Lens 2. We're not given the type of lens, focal length, or image location. However, we do have the magnification. The fact that the magnification is negative, we could immediately determine that the image must be real, because the negative sign implies that it's inverted, and its magnitude, which is 0.25, means that it has to be smaller. Only a converging lens can actually make this happen. The image location is 4 centimeters. I could use the thin lens equation to get the focal length. The focal length f2 is 3.2 centimeters. Since we're already giving the magnification, we can immediately get the image characteristics. With m2 being minus 0.25, the negative sign tells us that it's a real and inverted image, and the 0.25 tells us that it's a smaller image. Let's draw the ray diagram. Putting in the numerical values into the ray diagram, the object is 16 centimeters from the lens, which is outside of 2f. The image should lie between f2 and 2f2, and you could see that our calculation shows that the image is 4 centimeters, which would be right in there. Lens 3, there's a lot of information. The focal point is negative, so we immediately know that it's a diverging lens. But because it's a diverging lens, the magnification should be less than 1. Also, we could see that the image distance is negative, which tells us again that it has to be a diverging lens, because it's smaller, that is. So I know that the image is virtual, and I know that it has to be erect. Let's go calculate all of these details. Starting with the thin lens equation, we could solve for the location of the object. Starting here, solving for S3, doing the algebra, we get a positive 30 centimeters for S3. From the magnification equation, we calculate the quantity minus S3 prime over S3, and we get a value of positive 0.33. That means then that the positive sign tells us that we have a virtual and erect image, and the 0.33 tells us that it's smaller. If you're looking at the ray diagram, we could see that the object is at 2f3 and the image is inside the focal point as expected.